My name is Katie, and today I'm going to give an introduction to neural networks and walk through some code that implements one. This talk is going to be focused on introducing some ideas underlying neural networks, so we're going to be using toy examples, but hopefully the ideas in this talk prove useful when you're encountering discussion of neural network approaches to solving more realistic computational problems. Should I go see Wonder Woman tonight? That is the question before us today. There are probably a number of factors that would play into this decision, but for the sake of building a simple model, let's just list three. Have I already seen Wonder Woman? Do I have too much Grace Hopper work to do? Probably yes, but we're just going to pretend for the sake of argument right now that that's a question. And is there someone who wants to go with me tonight? A decision in this sense is a classification problem. It takes inputs and then tries to use the inputs to compute an answer, which in this case is a binary yes or no. A lot of other interesting problems that are very hard to solve algorithmically, and until recently were very hard to solve at all, are also classification problems. An example of a classification problem that's challenging to impossible to solve algorithmically is recognizing handwritten digits. What set of steps would you dictate to say that a digit is a 4, not a 9? It's really hard to imagine explicit instructions that would do this reliably. And yet human brains can do it effortlessly, and now computers can too, by looking to the biology of the brain for inspiration. This is a neuron. It takes inputs from other neurons at its dendrites. It has to sum them all up, and once those inputs reach some critical threshold, the neuron fires a signal through its axon. This is a binary decision, fire, don't fire. It is possible that different input neurons have different amounts of influence over this decision. Maybe some of the input neurons have axon terminals that connect to more than one dendrite on our candidate neuron. Those would be heavily weighted neurons. And maybe some of the input neurons are inhibitory. That means they have negative weights, and they make it less likely that our candidate neuron fires. After it takes in all the information, it makes a decision, fire, don't fire. This is also a neuron, a more abstracted one. Like the biological neuron, it takes inputs, sums them up, and then decides on an outcome. The particular neuron we're describing right now is called a perceptron, but we'll meet a different kind of neuron later in the talk. So let's imagine that my neuron is modeling my decision about whether to go to Wonder Woman. Some of the factors might be more important, and some of them might be less so. Just as biological neurons can weight their inputs differently, so can abstract neurons. So one question I had was, have I already seen Wonder Woman? If I've seen Wonder Woman, I'm less likely to want to go. So let's give this input a weight of -1. When it fires, it can only send a 0 or 1, but if it sends a 1, that number is multiplied by the weight, and our go to Wonder Woman neuron receives -1. If I have too much work to do, I'm really not going to want to go, so let's give that a larger negative weight. And if someone else wants to go tonight, it will encourage me to go, so let's say that gets 3. I also have some inherent bias towards not doing anything in particular, so let's say that my inputs have to add up to at least 2 to get me to go to Wonder Woman. So now let's say I have seen it, and I don't have too much work, and someone else wants to go. That's actually not big enough to be greater than my bias, and my output neuron doesn't fire. But if I haven't seen it, and I don't have too much work, and someone wants to go, that adds up to 3, and I go to Wonder Woman. Neural networks can also have more than one output and layers in between inputs and outputs that encode more complicated features. For example, right now in my Wonder Woman network, too much work and someone wants to go exactly balance each other out. But maybe whether I've seen it is really important and heavily weighted when I have too much work, but less important when I don't. That's the kind of feature that could be encoded in a hidden layer. We never tell the networks these kinds of rules. It's their job to learn them. And neural networks can be arbitrarily complicated and learn arbitrarily complicated rules. So how do neural networks learn? We give neural networks training data, pairs of inputs and outputs. They then complete a series of 4 steps, which I'll talk about at a very high level here, and then describe in more detail in our code example. So first they initialize their weights and their biases. Then they use those weights and biases to make a prediction. Then they figure out what direction to adjust those weights and biases in order to get our prediction closer to the known correct output. And then finally they return to step 1 with the new weights and biases and repeat that a bunch of times. Step 3 is definitely glossing over some things, so let's discuss the process in more detail. All the code you're going to see comes from Andrew Trask's 11-line neural network. The code is going to train on this set of inputs and outputs that you see here. Every row is a training example, and every column is a different neuron, 3 input neurons and 1 output neuron. These inputs and outputs have the same form as my Wonder Woman question. For example, on the bottom line, 0, 1, 1, if I hadn't seen the movie, I had too much grease hopper work to do, and I had someone to go with, I would have had an output of 0 and I wouldn't have gone. Not every one of these training cases perfectly maps onto my example, but the format of the 3 input neurons and 1 output neuron is the same. So our goal in training the network is to discover a set of weights so that each of these rows of input sums to the correct output. In this very simple example, we're going to ignore bias. So let's start with the code. 11 lines. First, we import the NumPy library, which stands for numerical Python. This is the library for doing matrix algebra. Then we define the sigmoid function. Let's take a short break from this code that we just started to explain why we're doing that. I mentioned earlier that perceptrons, neurons with binary inputs and outputs, were only one kind of neuron. For our purposes, we are going to want our outputs to vary between 0 and 1. During training, we're going to want to be able to tell our network how far off it is when it tries to make a prediction. If we could only tell it 0 or 1, whether it was right or wrong, we wouldn't know how to adjust. So we're going to feed those outputs through the sigmoid function before sending them on. As you can see from the form of the sigmoid function, when the independent variable is large and positive, the function approximates 1. So if the weighted output of the input neuron is large and positive, the output neuron will get something close to 1 from that neuron. On the other hand, if the magnitude of the independent variable in the sigmoid function is large and the sign is negative, the function approximates 0. So if the weighted output of the input neuron is very negative, it will send something close to 0 to the output neuron. There's more variation in the middle for weighted inputs closer to 0. Okay, these lines initialize our data to the input and output we saw before. Then we seed some random numbers and initialize our weights to a 3x1 column matrix of random numbers with mean 0. In the next lines, we're going to start to train. Should have had a Rocky montage here. Starting off our loop, which we're going to go through 10,000 times. We initialize L0 to be our inputs, and this variable never changes. It's just calling it L0 emphasizes that our inputs are also a layer in the network. The next line is our prediction. MP.dot performs matrix multiplication of the inputs and the randomly initialized weights. I put a little example of what matrix multiplication might look like in case you're not familiar with linear algebra. The example has fictional weights. At the bottom are the calculations to generate the first element in the answer by taking the weighted sum of the first training example. It's just the same as what we did before with Wonder Woman. Every input neuron, every column gets a weight, and we do the same for each training example to generate the rest of the answer. Once we have that result, we call the function non-lin to run those weighted sums through the sigmoid function. Now we have a prediction for each training example. And finally, we compute the error for each prediction, the right answer, y, minus our prediction. In other contexts, we might call this the cost function. We're trying to minimize the cost function, or get y minus L1 as small as possible. In this line, we're figuring out how we're going to update our weights. Now we're going to take our weighted inputs and run them through the derivative of the sigmoid function. So the main curve on this graph just shows the sigmoid function again, and the derivative is going to be the slopes of those lines that you see tangent to the graph, because the derivative is the rate of change in a function. When the sigmoid function is approaching 0 or 1, the tangent line, the rate of change, is nearly horizontal, and the rate of change gets very small near 0. And we already said that the sigmoid function was going to approach 0 or 1 when we had very negative or very positive weighted inputs. So multiplying by the derivative of the sigmoid function is like saying, hey, when we have these large magnitude weights, it looks like we've gotten pretty sure about this in the course of all our iterations. Don't update much based on this training example. But if we're less sure, if we're in the middle of the graph, update more. And then we multiply each element of that result times the error, which only amplifies that effect. Error is small near 0 or 1 and larger in the middle. When error is small and the derivative of the sigmoid function is small, we won't update much because their product is really small. But when our weighted inputs are nearer to 0, our error is larger, and the derivative of the sigmoid function is larger, then we'll update more. We call the result of this calculation the delta, and we're going to use this for the update in the next step. Now we update the weights. We're computing the weighted sum of the original input with the deltas we just calculated. This is another example with fictional deltas and updates below the code. Over on the left, we transposed our inputs. Now each row is an input and each column is a training example. Then we have a column of weight deltas. Each one of the deltas corresponds to one of our training examples. So to compute the amount we're going to update each weight, we're just going to calculate the sum of the updates for each training example, weighted by whether that neuron had fired in our training example. When it didn't, it just had no effect. If a training example got really close to the right answer, its delta will be very small, like in the top of the deltas column. So for example, to get the weight update for the first neuron, we multiply 0 times negative 0.0001, add 0 times 0, add 1 times 0.5, add 1 times negative 0.02, and get 0.48. Okay, let's run through just those loop steps again. We take the sums of the input neurons, weighted with our randomly initialized weights. We feed those to the sigmoid function to get values between 0 and 1. Those are our predictions for the values of our output. Then we calculate the error on those predictions. Then we go back and calculate the derivative of the sigmoid function for each of our weighted sums of input neurons. And then we multiply that by the error. That's the amount we're going to update our weights. Both the error and the derivative will tend to be really small when we have confident predictions, when our weighted sums are large and the sigmoid function is close to 0 or 1. So under those circumstances, the weights won't update much. But if our error is larger and the derivative is larger, our weights will update by a greater amount in the direction that makes the error smaller. We hope that at the end of 10,000 iterations, we will train the network so that it has a set of weights that produce the output 0011. If we give it a test input data for which we don't know the answer, it should be able to tell us, at least if it had more training examples than we have. Let's run it and see if it works. So here's our code. It's pretty small. Oh, you're getting a preview of it working. But here is this entire code. So there's some comments in it. Oops, that's the one with all the printing. Well, that's fine. So there's some comments in it and a lot of print statements that I put in to show its progress. But the actual lines of code are just 11 lines. And so we'll run it. And there, it's less suspenseful since you had already seen the answer. But we see that our first two results approximate to 0, and our second two results approximated to 1, just as we hoped would be true. Oh. And I will attempt to get out of here and back into my presentation. I'm back, thank goodness. That worked. We saw the weights that it discovered. So this was obviously a simple example designed to make the details of the code a little more approachable than they would be if you started with a much harder problem. We didn't discuss all of the kinds of neurons, a lot of the challenges in tuning neural networks, the many different kinds of implementations or problems to solve that aren't classification problems like prediction. So many things we didn't discuss. But the basic conceptual approach outlined here can provide a foundation for understanding problems more elaborate than whether I should go to Wonder Woman, like how to make your Shiba Inu psychedelic. And these are the sources that I found very helpful in this talk. Thank you for listening.